Hello. Today we're going to go over 16.6 and we are covering parametric surfaces and then areas. I say their areas, but it's really the areas of the surface that we parametrize. So we've been working with space curves so far, and the space curves, those were R of t, and we use those in order to calculate line integrals. What we're going to be doing now is preparing to work with surface integrals. And so we'll still need to have some sort of vector representation. But now what we're going to be doing is we're going to be taking the surface of a solid, which would have three variables. You could think of something like a sphere, x squared plus y squared plus z squared equals 4, right? That would be a solid. We want just the surface of the solid, not the insides. And those have three variables, okay? And so what we're going to have to do is parametrize the surface, since a surface is technically two-dimensional, if we want to get area. And so we need to get down to two variables. And so we're going to parametrize, we're going to get a vector function of two variables that represents the outer region of some given solid, okay? One thing that we have to realize is that surface area is a 2D measurement. It's just the outside of a solid, okay? Not the inside stuff. Let's see. So what we're going to be doing with our parametrization is trying to fix one of the variables in some way, shape, or form. Every situation is unique. There is no one way that works for every single solid that we work with when we try to parametrize to the surface of that solid. But in a sense, we're going to get rid of one of the variables. So here's kind of what's happening after we parametrize. What a parametric surface or a parametric vector, R of uv, does is it's going to take points uv from some domain. Okay, and notice that that domain is a two-dimensional domain. And what it's going to do is take all those values uv from that domain, plug them into a vector, and that vector is going to literally shoot out points on the surface. And as you can imagine, there's probably an infinite number of points on any given surface, just as there's an infinite number of UV pairs in a domain D. So we're going to take those infinite number of pairs, plug them into the vector. The vector is going to shoot out all the points that make up the outer portion of a solid, which is called the surface of the solid. Okay. Let's see. So there are situations where we need to express the surface of a solid as a function of just two variables instead of three. And what they are, well, there's several, but the most important ones for us are going to be being able to find the equation of a tangent plane as a vector or not as a vector, as a parametric surface. And then we're going to be using that in order to be able to calculate the surface area. And I'll get more into detail on that in a little bit. So when we parametrize a surface, what we're going to get is some function R of uv, and each of the components of that function is going to itself be a function of uv. Maybe, it could be a constant, it could be a function of just one of those letters, but at the most, each of those components would be a function of u and v. We still call them the x component, y component, and z component. Those are the parametric labels that we give each of the components of our vector. And I think I said all of that. Okay, so let's go ahead and see if we can identify and sketch a surface with some vector equation. So we're given here R of uv is equal to a vector with components 2 cosine of u, v, and 2 sine of u. And we want to know if we can actually identify what this is. What is this surface? And it's not blatantly obvious when you look at it. So what I tend to do is look for relationships. So I'm noticing that the x component is 2 cosine and the z component is 2 sine of u. And so there's a relationship between x and z, okay? I'm noticing, so if this is x, this is y, and this is z, then I could first say, well, what is x squared plus z squared going to equal? Well, I'm going to go ahead and plug in 2 cosine of u. If I square that, I get 4 cosine squared of u. And if I square the z, I get plus 4 sine squared of u, which is 4 times cosine squared of u plus sine squared of u. And cosine squared plus sine squared is 1, so I just get 4. Okay, so what we have is the relationship between x and z is a circle of radius 2. And it's x squared plus z squared is equal to 4. Okay, but y wasn't involved in all of that, and y is part of the vector function that we have. Another way to interpret that, since y was not part of the circular relationship, y is kind of independent of it. Like y gets to be whatever it wants to be, while x and z have a circular relationship. So y is just v and is independent of the circular relationship between x and z. Okay, so what we could think about is we're going to let v take on constant values. And then let's think about what we end up getting. Okay, so in the case where y is equal to v is equal to 0, that would be right at the origin. And what x and z are doing at the origin, I'm going to have to give myself a little bit more to my octant. So what x and z are doing at the origin is they have a circle of radius 2. So let's get some tick marks on here. And go ahead and draw a circle of radius 2. Hopefully that looks like a circle that's on the xz plane, because that's what it is. So y was 0, or v was 0, and x and z played in a circle. They're completely independent of each other. And so I could pick some other y value. I could say, for example, let's go ahead and pick y equals 4. Okay, we're out here at y equals 4. What are x and z doing? Well, x and z are still forming a circle of radius 2. So let's see if I can do that one. That's going to be a little bit harder because I have nothing to guide me. Something like that. All along the y-axis, in fact, I'm going to be getting circles of radius 2 from x and z. So x and z are going to form circles no matter what y does. So y can go ahead and take on all the constant values that it wants to, but x and z are still going to form a circle. And so what we're seeing here is a cylinder, right? And this is a cylinder that runs parallel to the y-axis with radius 2. That's it. So it takes a little bit of thinking through it. The good thing is that these three-dimensional shapes should not be new. We started working with them on day 1 in 12.1, and we've continued to work with them all semester. So this is what we get. All right, so we need to look at what some of the common parametrizations are, and many of these are on your formula sheet. The very first one is planes. So we learned way back in 12.5 that a plane needs a position vector, r0, and that represents some point on the plane. And then it needs 2 non-parallel vectors, A and B. In other words, they're not parallel to each other. And those are also on the plane. Okay. And here's what we get. So if we have two vectors that are on the plane and not parallel to each other, and we have a point r naught or p naught on the plane that we can represent with r naught, then the equation of a plane is just r of u of v equals r naught plus ua plus vb. Technically, you can switch the a and the b around. That doesn't really matter. B could go with U and A could go with V, but in general, this is our form. Now notice that each component is a linear function of U and V. Remember, the x naught, the a1, the b1, those are all just numbers. And so what we've got is a representation, a linear representation in each of the variables. And altogether, those are going to give us points that are on a plane that has a point, P naught, and two parallel vectors, A and B. If we want to get a common or a parametrization of a sphere, if we're working with the surface of a sphere, then we will have a fixed radius, okay? That means that rho, the radius of a sphere, is not varying. We are picking one value for rho. It is the value for rho that gives us the outer portion of the sphere. So we're removing the need for rho to be a variable. Rho is fixed, okay? It's a fixed constant. Okay, so we can let rho equal A. Now, in a real situation where we're working with parametrizing these, we'll have been given a sphere, we'll know what the radius is, and we'll let rho equal whatever that radius is. Okay, now what's not fixed is phi and theta. We still need phi and theta to sweep out a sphere. Okay, so we're still going to be using what looks like spherical coordinates. Because they are very convenient given that they have only two variables in them now with rho being fixed. So we've got the x component, a sine phi cosine theta. We have the y component, a sine phi sine theta. And we have the z component, a cosine phi. Remember, a is the value of the radius and it is fixed. It is not varying. We only have phi and theta varying. Phi goes from 0 to pi, and theta goes from 0 to 2 pi, and that sweeps out an entire sphere. These are not spherical coordinates, okay? This is a parametrization, and that's it. We happen to use what we know about spherical coordinates in order to, it's like we're borrowing spherical coordinates in order to come up with a parametrization. But when we get to calculating surface area, and we have parametrized a sphere, and we're trying to find the surface area of a sphere, don't let these fool you. Like, don't change your differential, okay? So that's going to be one of the things to be extremely cautious of, right? We have a parametrization that looks spherical because it is giving us a sphere. But any integration with that parametrization will not introduce a differential that has that rho squared sine phi. Okay, that's not going to happen at all. All right, then we have a cylinder. A cylinder is also a very common thing that we will need to parametrize, and we actually just dealt with one. Notice in the one I have right here, we have the x component is a cosine theta, the y component is a sine theta, and the z component is just gets to be z. So the parameters are theta and z, whereas the radius value of the cylinder is fixed at a. Okay, so we let r be a. It's not going to vary. We only want the surface of the cylinder. We don't want the inside. Okay, now notice in this one, x and y had a circular relationship because one was cosine, the other one was sine. Z was just getting to be z. Compare that to what we did above, where x and z had the circular relationship and y was the one that got to be whatever it wanted to be. In this one, we went ahead and we used u and v. In the one below, they're using theta and z. Whether you use u and v or theta and z doesn't really matter. In this one that I'm looking at right now, if I wanted to switch to like theta and one of the other variables, I would use theta and y as my parameters. So we could use theta and y as parameters here. So this is just kind of a note, an aside that's not part of our problem, but we could have said r of theta y is equal to a vector with components 2 cosine theta y and 2 sine theta. So it still looks the same, just different parameters. It means it's exactly the same thing. We just use different letters. Okay, don't let the letters trip you up. All right, another common parametrization after the plane, sphere, and cylinder are explicit functions. And honestly, these truly are the best we can hope for. Now, we've used these words, explicit functions, a lot this semester. And my hope is that you all are on board with what an explicit function is. It just means that one of the variables is written as a function of the other variables, and it only shows up in that one place. So for example, if we have z is equal to a function of x and y, that means z is on the left and only x and y are on the right. That's an explicit function. And if we have that situation, then what we would say is, well, then, okay, x and y just get to be themselves, and z will be the function of x and y. So parametrization would be r of xy equals the vector with components xy and f of xy. There's like no work involved right there because we're given the explicit function. We just need to know where to put it in the components. Similarly, if we have y equals a function of x and z, then the parameters are x and z. X and z get to be themselves while y has to be the function of x and z. And last but not least, if x is a function of y and z, then y and z are the parameters, and x has to be a function of those parameters. Okay, so let's just state that. So here, x and y are parameters. In the second one, x and z are parameters. And in the third one, we have y and z are parameters. Okay, so those are the most common parametrizations that we'll be working with. So work with them, practice them, know how to use them. Okay, so I want to go through a few examples where we're trying to identify what surface we have. I want you to keep in mind there are actually 7 more examples of this in your textbook. So we're doing a few here, but know that there are more, and that's meant for you to practice with and get comfortable with. Okay, so take advantage of that. All right, we're given here r of uv is equal to a vector with components u plus v, 3 minus v, and 1 plus 4u plus 5v. This looks like a plane. And remember that a plane, r is equal to r naught plus u, my writing is off today, u a hat plus v b hat. Okay, so maybe let's rewrite our plane in terms of 3 vectors, okay? So it looks like for r naught, in the first component there is no r naught, so let's put 0. In the second component, that 3 is part of r naught. In the third component, that 1 is part of r naught. So there's our r naught. Plus, I'm going to write my u terms. So my second component, or my second vector, I have a u from the first component. I have a 0 from the second component. And I have a 4u from the third component. Then we have the v vector and its coefficients. We're going to get v from the first component, minus v from the second component, and 5v from the third component. And finally, I'll just factor out the u and the v. This is equal to the vector 0, 3, 1 plus u times 1, 0, 4 plus v times 1, negative 1, 5. Okay, so this is a plane that contains the point 0, 3, 1 and two vectors 1, 0, 4 and 1, negative 1, 5. So my goal right now is to try to rewrite this equation of the plane in terms of x's, y's, and z's. So I have to recall that the equation of a plane comes from looking at the dot product of a normal vector with r minus r naught. I'll rewrite those actually as the vector x, y, z, that's r, minus the vector r naught, which is x naught, y naught, z naught. And we set that equal to 0. And then we'll be able to come up with the equation of our plane. Now we need a normal vector for our plane, and we could get that by looking at the two vectors that are on the plane and not parallel to each other. If we were to take the cross product of those two vectors, we would get a normal vector to the plane. So our normal vector will equal the cross product of 1, 0, 4 and 1, negative 1, 5. So we need to calculate that cross product. 1, 0, 4, 1, negative 1, 5. In my first component, I get 0 minus a negative 4. In my second component, I get a minus 5 minus 4. In my third component, I get a negative 1 minus 0. This simplifies to be the vector with components 4, negative 1, negative 1. All right, so this is normal to the plane. If you find yourself still struggling with calculating a cross product, I'm going to strongly recommend that you practice, because we're going to be using them a lot for the rest of the semester. Okay, so we have a normal vector to the plane. We have a point on the plane, the 0, 3, 1, so we can go ahead and come up with the equation of the plane. We've got our normal vector, 4, negative 1, dotted with r minus r naught gives us x minus 0, y minus 3, and z minus 1. This is set equal to 0. Doing the dot product, I get 4x minus in quantity, y minus 3, minus in quantity, z minus 1 is equal to 0. This becomes 4x minus y minus z plus 3 plus 1 is equal to 0. And finally, we have 4x minus y minus z is equal to negative 4. Okay, so interestingly, right, we've got a vector representation of the surface of a plane, and then we have the actual x, y, z representation of the plane. All right. The next one is r of st is equal to a vector with components s cosine of t, s sine of t, and s. Let's see what this is. So it may remind you of the cylinder, but this one is not the cylinder. Let's see why. All right, I'm noticing that in my x component I have a cosine, and in my y component I have a sine. I'm also noticing that z is just a number, s. Well, actually, it's not a number, it's a variable s. So our parameters are s and t. So with those cosines and sines, I'm going to go ahead and look at what is x squared plus y squared. Well, when I square each one, I get s squared cosine squared of t plus s squared sine squared of t. I can factor out the s squared, leave behind a cosine squared of t plus sine squared of t, and that's just equal to s squared. But s is equal to z. So if I have x squared plus y squared is equal to s squared, that means that x squared plus y squared is actually equal to z squared. Because there are no restrictions on s in this parametric surface, we can see that z can take on plus or minus the square root of x squared plus y squared, which is the full cone, right? Because we can get the positive and the negative solutions for z, meaning we'll get the top half of the cone and the bottom half of the cone. Okay, so it's quite different than how we work with the plane, right? So each time you come across a parametric surface, you have to kind of be prepared, knowing in advance, like, okay, so I think this is a plane. Let me start working with it like it's a plane. Or I think this might be cylindrical or cone or something round. So I'm going to start working with it as though it's something round. All right, let's look at C. In C, again, I'm seeing cosine and a sine. My first component, x, is equal to the u squared. Y is u cosine v, and z is u sine v. So I'm seeing y and z have the cosine and sine. I'm going to go ahead and look at what does y squared plus z squared give me. That's always going to be your start when you see the sine and the cosine. So I go ahead and substitute what they are. This is going to give me u squared cosine squared of v plus u squared sine squared of v, which is equal to u squared times cosine squared of v plus sine squared of v, which simplifies to just u squared. But u squared is x. So what I have here really is y squared plus z squared is equal to x. Okay, this looks like it is a paraboloid. So this is a paraboloid that opens along the positive x-axis. Okay. All right, so make sure that you're practicing some of these, getting comfortable with these. We've done 3 here. There's more in the book to practice, and there's some in the homework as well. But I would strongly recommend not just doing the homework, but also making sure you can really understand these from here in my notes, and also those that are in the textbook. All right, number 2, we need to now start with the information in X, Y, and Z, and work our way towards coming up with a parametric representation for the surface. So in A, we're told to find a parametric representation for the plane that goes through the point 0, -1, 5. That's going to be our R naught, and contains the vectors 2, 1, 4 and -3, 2, 5. These are going to be our A and B vectors that are on the plane. So what we have to remember is that the plane is R of UV equals R naught plus UA plus VB. And then we just plug everything in. So this gives me the vector 0, -1, 5 plus U times 2, 1, 4 plus V times -3, 2, 5. And I can rewrite this as one vector. It will be first component is just 2u minus 3v. Second component is -1 plus u plus 2v. Third component is 5 plus 4u plus 5v. And that's it. That's the equation of our plane. Not too hard there. As long as we have a point and 2 vectors, we're just plopping things in. Okay, here we have the part of the ellipsoid, x squared plus 2y squared plus 3z squared equals 1, that lies to the left of the xz plane. This is a tricky one, and it's tricky because we don't know a good parametric representation for an ellipsoid. We weren't given an ellipsoid as one of the common parametrizations. And so that's problematic. What we are given here, though, is that it lies to the left of the xz plane. So what we have to realize is what implications there are to something being just to the left of the xz plane. The implication, this implies that y is negative, because that's where y would be negative. And so what that gives us is some freedom. We can actually solve for y, and I'll write this. We can solve for y as an explicit function of x and z only because y is strictly negative. If we did not have that restriction on y, we would have to come up with two parametric surfaces, one that took care of the positive solution for y and one that took care of the negative solution for y. And that would be problematic because then we would be dealing with, well, we're leading our way to surface areas and then surface integrals. And so it would lead us to having to deal with two of those in order to get what we need. Okay, so you have to keep in mind that when you're taking square roots, you normally get two solutions, plus and negative. And if there's nothing that's telling you which one you should take, then you have to take both. All right, we have something telling us that we should take the negative, so we're going to take that. So let's go ahead and solve for y in our equation. We have 2y squared is equal to 1 minus x squared minus 3z squared. So y squared is equal to 1 minus x squared minus 3z squared over 2, which means that y is equal to the negative square root of 1/2 times 1 minus x squared minus 3z squared. Okay, so we have y as an explicit function of x and z. That means x and z will be our parameters. Okay, so we're going to take this and we're going to build our vector parametric surface for the ellipsoid. So r of xz will equal a vector with components x. Since x is one of the parameters, it gets to be itself. Y will be the negative square root of 1/2 times 1 minus x squared minus 3z squared. And then z is one of the parameters, it gets to be itself. And that's it. That is our parametrization of the part of the ellipsoid that lies to the left of the xz plane. Now, if they had said that it lies to the right of the xz plane, the only difference would have been taking the positive square root. All right, now in part C, we want the part of the sphere that lies above the cone, okay? So just to give you a quick visual of that, I have to draw the sphere first. I'm only drawing a half sphere because they're telling me it's only the portion that's above the top half of a cone. So this is the region that we want. That's it. Okay. So it's got bounds that are created by the cone, but the cone is not actually going to be part of our parametrization. We are parametrizing the sphere. Okay, so we parametrize the sphere. The cone helps provide us with bounds for phi. That's all that it does, okay? So we were told earlier that when we come up with a parametrization for a sphere, we're going to use the parameters r of phi theta. And let's see, so we have, our sphere has a radius of 4. So I want to say rho is equal to 2. That's our fixed radius. So when we come up with the components of our vector, the radius is 2. And then for the x component, we know that we have sine of phi, cosine of theta. The y component is the rho, which is 2, and then sine of phi, sine of theta. And then my z component will be the 2 cosine of phi. So I'm borrowing spherical coordinates, but they're not fully spherical coordinates because rho is fixed at 2. Now, we need to put some bounds on theta and phi because we don't want the full sphere. This guy that I just wrote right here would parametrize the entire sphere if I didn't write anything else down. So we need bounds in order to only get the part that is above the cone. This is a standard cone, and a standard cone has an equation phi equals pi over 4. And so that is actually going to be the upper bound for our region. We're going to have that phi can start at 0, but it must stop at pi over 4 because we're not getting any portion of the sphere that's outside of the cone. Now we are still going all the way around, and so that means that theta is still going to go from 0 to 2 pi. All right, and that's it. Not too hard, but you do need to know these these common parametrizations and what's fixed and what's not. Okay, the next topic is tangent planes. So now that we can parametrize a surface, we have to be able to parametrize a tangent plane to a surface, as we're going to have to use that in order to calculate surface area. Plus, it's going to give us one more way to come up with the equation of a tangent plane, as if we needed another way. So when we're coming up with a tangent plane, we have to remember that we need a normal vector and a point. Okay, so if, how do I want to say this? If R of uv parametrizes a plane or a surface, at a point, then it will also parametrize, well, let's say, I don't want to say parametrize, it will also, how do I want to say this, go through the point of tangency for the tangent plane. Okay, so I've got a little picture drawn right here. This is a surface, S, and we've got a point right here, that's P naught. And so right at P naught, we've got this parametrization for the entire surface, but we're fixing on one point on the surface, P naught. Now, at that point, if we were to take our surface function, our parametrization function of the surface, and find the partial derivatives of it, the r sub u and the r sub v, those partial derivatives are going to be vectors that are tangent to the surface at the point. Now notice, like you can imagine maybe that if we were to kind of expand this, those vectors are also parallel to a tangent plane at that point, okay? So in a sense, we should be able to parametrize a surface and then find the first partial derivatives of that parametrization and know that those vectors that we find are actually parallel to a tangent plane, then we can take the cross product of those and it would give us a normal vector. And that normal vector, as I just stated, would be the first partial with respect to u crossed with the first partial with respect to v of the parametrization. So that's the main idea here. P naught would be the point, and the cross product of r sub u and r sub v would be the normal vector. And so then we could put this all together and we have a new form for our equation of a tangent plane. Before, when we were looking at equations of tangent planes, we found that the gradient vector would serve as the normal vector to a tangent plane. Now that we're working with surfaces and we have parametrizations of surfaces, we have a whole new way of coming up with the equation of the tangent plane. So we're going to go through an example where we find an equation of the tangent plane to the parametric surface that's given. X is equal to u squared plus 1, y is equal to v cubed plus 1, z is equal to u plus v. So this is the parametric equations of our parametric surface. And we want to find the equation of the tangent plane at the point 5, 2, 3. So this right here is our P naught. And so that's going to allow us to say, okay, R naught is the vector 5, 2, 3. Okay. Now I want to find, if I go ahead and put this together, this may help some of you watching this. R of uv has components u squared plus 1, v cubed plus 1, and u plus v. So I'm just putting it in the vector form. Now, from above, I know that I need r sub u. R sub u, the first partial of r with respect to u, first component will give me 2u, second component will give me a 0, and the third component will give me a 1. R sub v, if I take the derivative with respect to v, the first component gives me 0, the second component gives me 3v squared, and the third component gives me 1. Now, I have a little trick with my cross products, especially from 16.6 on, because we calculate so many of them. I go ahead and it's a little bit of a cheat. I go ahead and above I put, and I don't even normally write these, I just write this for you. I imagine that they're there. My I, J, and K, and I've written my R sub U above my R sub V so that I can see things in an order of how I would write a determinant. So by writing it this way, I can easily come up with R sub U cross R sub V without having to rewrite things. So I have to remember kind of the order of things. We're going to have this product minus that product in our I component. So we end up with 0 minus 3v squared. Our j component, we have 2u times 1 minus 0 times 1. Our k component, we have 2u times 3v squared minus 0. So this simplifies to be minus 3v squared minus 2u and positive 6uv squared. Okay, so let's go ahead and come up with what this value actually is. So we don't have a u and a v value. This is where things get a little bit weird. this normal vector is a function. We need it to be a vector with just numbers. Now, the reason that it is a function is because we took the parametric surface and we're not even fixed at a point. We just went ahead and we took partial derivatives. Notice that the partial derivatives are also vectors with functions in them. So those are telling us what the tangent vectors to the surface are anywhere on the surface. But if we pick a particular u and v value, then we can find where on the surface, like one particular point on the surface. So we need a u and v value. And so that becomes the difficult part. To find u and v, solve, and here's what we're going to do. We're going to solve, we're going to take our r of uv, which has components u squared plus 1, v cubed plus 1, and u plus v, and we're going to set it equal to the point, because they gave it to us in x, y, z, 5, 2, 3. So we're going to equate x components, y components, and z components, and that's going to allow us to solve for the u and v that make this true. So the first equation, u squared plus 1 is equal to 5, which means u squared is equal to 4, which means u could be plus or minus 2. Hopefully one of the others tells me which u I need. The second equation says v cubed plus 1 is equal to 2. So v cubed is equal to 1. There's only one cube root of 1, which is going to be 1. So v is fixed. Then we have the third equation, u plus v is equal to 3. Well, I do know v equals 1 for sure, so I'll plug that in. U plus 1 is equal to 3, so u is equal to 2. Okay, these are the values I want. I'm not going to take that negative 2 because it only satisfies equation 1, not equation 3. So u is 2, v is 1. That tells me that my normal vector, I'm calculating it at 2, 1. It's going to be negative 3 times 1 squared, negative 2 times 2, and 6 times 2 times 1 squared, which simplifies to give me a vector with components negative 3, negative 4, and 12. This is my normal vector. So this is the normal vector at 5, 2, 3. Okay. If I had been given a different point, a different XYZ point, then I would get different UV values. Okay. So this is particular to our point. All right. Now our tangent plane, we can finally come up with, we've got our point, we have our normal vector. So our tangent plane is going to be the the n, which is negative 3, negative 4, 12, dotted with r minus r naught, which looks like, remember r is x, y, z, and r naught is x naught, y naught, z naught. So this looks like x minus 5, y minus 2, and z minus 3 is equal to 0. And we could go ahead and distribute, do the dot product, don't just leave it like that. So it's negative 3 times x minus 5 minus 4 times y minus 2 plus 12 times z minus 3 equals 0. And we could simplify this just a bit. We get negative 3x minus 4y plus 12z. I have a plus 15, a plus 8, and a minus 36 is equal to 0. And just one more simplification. We get negative 3x minus 4y plus 12z is equal to, So 15 and 8 is 23, minus 36 would give me a negative 13, which becomes a positive 13 on the other side. All right, that's our tangent plane. It was a lot of work, but we're starting with a parametric surface, and that's all we have. So we've got to be able to come up with tangent planes regardless of whether we've been given the equation in x, y, and z, or if we've been given the equation in terms of a parametric surface. Okay. All right, I'm going to stop right now because this video is approaching an hour. We've covered so far how to parameterize a surface and then how to come up with the equation of a tangent plane. In the next topic, we're going to cover surface area and work through a few examples. In the meantime, if you have any questions, please reach out.